So hi everyone, welcome and thanks for joining us today. We have Prof. Louis Bigo from University of Lille, France, who stopped by Singapore to visit us. So first of all, I hope you can hear me online. There's a few people on Zoom. So if you don't, just send a chat message and I'll try to fix that. So to introduce Prof. Louis very briefly, I actually met Louis when I was finishing up my postdoc in San Sebastian in Spain, and Louis was a postdoc, and we were both working on a project on music generation. After that, I think Louis went to University of Lille, where he uses mathematical and statistical machine learning methods to analyze and model music. So he's very much an expert on music generation. So today he's going to be sharing about how we can use language modeling techniques for music. So I'm very excited to hear what you have to say, Louis. So I'll leave the floor to you.
Okay, thanks. Thank you. Thank you very much. Just put that. Okay. Great. So thank you very much. I'm really happy to be here and to stop by this wonderful place. We'll begin right now with a small musical game. I'm going to let you hear just 1 second of music, a short excerpt, and let you guess what could come next. Okay, so the little game. So 1 second of music and try to imagine what is coming next. So thank you. Great. Very good. Good in blind test. I love blind test, by the way. But anyway, so yeah, maybe some of you recognize the first second of Shape of My Heart of Sting. And so here, what is coming next? Oh, no, it's stuck. Okay, let's. Okay. So would a computer be able to predict what is coming next, even if you never heard the song before, if you didn't know it before? So that's one of the questions we're going to discuss in this talk through different research projects. Okay, sorry, it's gonna come. It's a little bit slow. Maybe I should plug my. Oh. Yes, I don't know if it's better to this. Okay. Yeah, okay. It's going to work. Yeah, so different research project that I'm working on in my team, in my research team, Algomus. So Algomus stands for Algorithmic Musicology. We are a research team based in Lille. It's a city in the north of France, a great city. And in our team, we are trying to elaborate computational models to assist music analysis and music composition. So this involves reflection on how to represent music from a computational point of view, and how to elaborate algorithms that could be based on machine learning, on system of rules, in order to process this data. So let's go back on a little bit of music, but my computer is still very slow, and I have to wait for the next, I don't know what's happening. Did it come or not? I didn't see my, no. What is happening? Okay, it's working. So yeah, another piece of music. So we're going to listen to 3 excerpts of a piece of music, and we're going to watch them also. Okay, so we just heard the song Take a Bow of the band Muse with the notes and the chords represented in a space which is called the tone net. It comes from tone network. And it was invented by the mathematician Leonhard Euler in 1739. And the idea of Euler was that the notes that are consonant, where they are played together, should be close one to each other in opposition to the musical score, for example. So, for example, here the C, E, G notes, which makes the C major triad, which includes the interval of fifths, of major third, and minor third, are close one to each other and make a compact shape. So, in this space, consonant chords are represented as compact shapes. And you can visualize the evolution of a piece of music as a shape which is evolving in the space and analyze this music with geometrical tools. And it's interesting to see that there is actually a large variety of musical spaces that have been elaborated by theorists in order to try to capture the singularity of music. And the idea being that when the music is represented in the space, then the property that we want to represent is revealed by the space. For example, it will be consonant for the tone nets. We got also three-dimensional, four-dimensional generalization of the tone nets, as the spiral arrays, tonality strip, voice leading spaces. I'm not entering in details here. Just the voice leading space are interesting. It's spacing the chords close one to each other when you have a parsimonious voice leading that lets you go from one chord to another. For example, on the piano, when you just play a triad and you just move one of the three notes from a very small move, which is really common in tonal music, then you get a parsimonious voice leading. And just iterating this move, you get like some typical moves in tonal music. So this would be, this kind of space would be convenient to see that. So the idea is to use the intuitive notion of space in order to try to describe a complex property in music, whether it's consonants or voicing or other things. And there's actually another intuitive notion that we tend to use to try to formulate the complexity of music, and it's the notion, the notion of language. No, it's fine, it's working. So yeah, we were talking about musical language. We sometimes say that music is similar to a language. And sometimes the expressivity of a melody almost give us a feeling that the melody is telling us something like a story or something else. And seeing music as a language is really convenient for computer scientists, because in computer science, we have many tools to process a natural language, and it's a whole field, which is called natural language processing. I'm sure that a lot of you are familiar with. And in natural language processing, we have tasks like automatic translation, content generation, summary generation, sentiment content analysis, lemmatization, etc. And it's a research field in which there have been a lot of progress these last years. And people in music research have had the wish to take advantage of this progress in order to apply this algorithm on musical data, starting from the hypothesis that music is similar to a kind of language. And also from a practical point of view, given the fact that the temporal nature of music facilitates its representation as a sequence of elements, similarly to the text, which is represented as sequence of words. Then melody can be represented as a sequence of notes, a harmonic progression as a sequence of chords. And we get tools in order to represent music with what we call tokens. Here's an example with a melodic fragment, when you have a pitch which is activated and then deactivated with time shift in order to go through time, etc. Another motivation, another justification to the application of NLP methods to musical data is that we have common tasks with NLP. So genre classification, content generation, style transfer, they are all tasks that make sense both in text and in music. And we have these data structures implemented too. So with my colleague, Michaela Keller, she's working in a machine learning team in my lab, but with no relation at all to music. She's only working on NLP. We've been discussing a lot, and we've been observing common points we get, or a different approach, even if the data are very different. And we wanted to have we started to collaborate in order to try to have a global point of view of this practice, a general point of view of this practice of applying language-based algorithms on music, and try to think about the adaptability, the performance, and the limits of applying NLP algorithms on musical data. So adaptability, for example, as we said, as music is temporal, it can be represented as sequence of elements most of the time. But music is often polyphonic. And when you have simultaneous events, like simultaneous notes, you will have to make an approximation if you really want to represent it as a sequence of elements. While the text, it's always really a sequence of words. You're unlikely to have two persons speaking at the same time in one text. So that's a limit. Also, NLP algorithms generally have been thought such that they could be trained with very large volumes of data, of text data, which are more easy to find. And in music, especially in symbolic music, we are often limited in terms of size of data. For example, if you want to model the style of Beethoven's symphony, you know that you have nine symphonies, and you know that you're not going to have one more. So you will have to deal with this. In terms of performance, we're thinking about evaluation measures because it's probably more feasible to evaluate whether an algorithm succeeds in translating, for example, English into French, than evaluating whether an algorithm succeeds in translating a classical piece into a jazz piece, for example. And this will, because this requires some subjective judgments related to aesthetics and this kind of things that this kind of problems we are familiar with in music generation. And regarding the limits, I like to talk about semantic because a lot of NLP algorithms have been elaborated with the wish to extract the meaning of a sentence, to grow up in abstraction and try to know what it's talking about. And applying this on music, we don't really know what it could correspond to because we don't have really a semantic behind. It's more difficult to talk about semantic behind a musical phrase. We're more talking about transmission of feelings, and we don't know that if we all perceive the same thing, it's more difficult. So that's a question also we are asking. And another limit is the polysemy. People in NLP know that polysemy is generally a problem. It's when the same word can have different meaning depending on the context. For example, if I say the word theater, it refers to an art, but it can also refer to a building, depending on the context. Of course, you will need the surrounding words to know in which case you are. And in music, if you isolate a chord or a note, it's really unlikely that it could give you some useful information. You will always need the context. So it's like we are perpetually, constantly in polysemy. So in this project, the first thing we wanted to try is to investigate one of the models which has been the most used lately in NLP, which is a transformer. So a transformer is a neural network which is based on the principle of self-attention. And the mechanism of self-attention consists in, is intended to capture long-term dependencies between words. So if you feed your neural network with enough volume of text, in the end, it's supposed to understand that in this sentence, the monkey ate that banana because it was too hungry. It would refer more to the monkey than to that banana, because monkeys are more often hungry than bananas, of course. So very quickly after transformer appeared, some people tried to apply them on music, and we were really wondering what this relation, this long-term relation, could mean in a musical score. So the music transformer was one of the first trials from the Magenta team. They also have nice visualization, which makes us wonder, what does this relation between notes really mean? Does it mean that some notes are justifying some others coming in the future? Are some not required by some other? And how does this work? So what we did, our idea was to feed the music transformer with a lot of music, train it with a lot of music, and then open the neural network and look at the coefficient to see if we can get some musical interpretation of them. So it can look really complex because deep neural networks are often compared to black box, and you don't want to open them usually. But in case of transformer, it appears that self-attention is quite easily visible because it's basically stored through what we call self-attention matrices. So for example, once the network is trained, if I give a new sequence to it, it will automatically compute self-attention between the different notes. And for example, here I have a melody fragment. It's the same here and here. And what I see in the matrix is only the attention, the corresponding attention for every pair of notes of the melodic fragment. So once the transformer was trained, we presented to him several sequences extracted from fugues from Jean-Sébastien Bach, and some of them included end of phrases, and some of them were not including end of phrases. And what we wanted to see if in self-attention values, and only in self-attention values, not in the original musical data, we could retrieve if yes or no there is an end of phrases. In other words, was self-attention able to understand the concept of end of a musical phrase? And by the way, an end of a musical phrase in classical music is often associated to the principle of cadence. If I'm sure some of you are familiar with this. And so we found out that it worked. So we've been training a very simple classifier, a logistic regression, sorry, with the self-attention values, not the original musical values. And with only the self-attention values, we had results a little bit above a random classifier, which seems to show that, yes, these self-attention values understand somehow what is the end of phrase. We did the same with another task, which was composer classification. So composer classification there is a lot of approach. And again, the goal was not to be close to the state of the art, but only to check if by taking only self-attention values, it was possible to recognize composer, to distinguish composers, if self-attention value includes this abstract stylistic information. So it worked for quite different composers, like for example, Chopin and Bach, and Mozart and Debussy are really different. And for a similar composer for Haydn and Mozart, as expected, it's working very badly because we are close to 0.5, which is the random classifier. But we still saw that, yes, there is some stylistic information. And of course, that's what we were expecting, but it was nice to see directly in self-attention values. So now in the following, I will focus on two repertoires of music. The first one is classical music, and the second one is pop rock music. So in classical music, there is a variety of stylistic codes that encourage us to assimilate classical music with a kind of language. And between and among these codes, there is the principle of cadence that I mentioned just before. So usually a cadence is defined as perceptive phenomena, which is used by the composer to indicate the end of a phrase. Something is finishing and something else is about to begin. There is different type of cadence, different categories, and the two main ones are perfect cadences and half cadences. Interestingly, cadences are often compared to punctuation in text. So the perfect cadence is compared to the dot, which indicates the end of a phrase. And the half cadence is compared to a comma, which indicates that something is finishing, but something else needs to begin. Otherwise, it would not make sense. So let's hear an example. Here we have the beginning of an impromptu of Schubert with two phrases. And the first phrase finishes with a half cadence, similar to a comma. And the second phrase finishes with a perfect cadence, similar to a dot. So let's try to feel this different type of closure feelings. So if we want to model computationally cadences, we need to look in theory what makes a cadence. So we'll use an example here. It's in a string quartet from Haydn. It's at the beginning of the piece. We can hear just this extract. It's beginning a few measures before. So I will just show you when the music arrives in the score, so you can visualize the cadence. So I'm pretty sure everybody felt the closure. So why do we feel that? Why can we say there is a cadence here? For a lot of reasons. The first, so we have voice leading phenomenon. The main one being the move at the bass, and that's usually the way cadence are defined. Even though there is a lot of other features. So the 5/1 move at the bass, it's a fifth moves downward, or it can be upward or forward, and it gives this feeling of resolution that we have in perfect cadence. We also have melodic moves at the upper voice here. So here we're in the key of C minor. So the sensible note is B natural, and it's called the sensible, and it's resolving on the fundamental, which is the C. So which also contributes to this sense of resolution. Of course, we have rhythmic feature and general, and it's really common that after a cadence we have a rhythmical, as it's the case here on 3 of the 4 voices. We have preparation chords. So before the 5th degree on the that we can see with the bass move on the bottom voice, we have generally a subdominant chord, which can be either a 2nd degree or a 4th degree. Here it's a 2nd degree, which appears what we call a 2-5-1, which is really common in tonal music, also in jazz, and which is very convenient to affirm a tonality and to announce where we are. So here it's announcing the cadence and the tonality of C minor. In accordance with the preparation chord, we have scale notes, which correspond to the scale, which is represented by the harmonic progression. So here's the notes of the C minor. So we identified 44 descriptors that are organized in these 4 categories. And so that's the work of Laurent Feistauer, who defended his PhD last year. And Laurent has implemented these descriptors so they can be computed automatically at each bit of the musical score. Therefore, the musical score is represented by vectors of high-level values. And Laurent used 2 data sets of music with annotations of cadence that were manually annotated by musicologists, quartets from Haydn and fugues from Bach. And he evaluated these descriptors by building a classifier in order to predict the occurrence of a cadence at each beat, depending on the values computed by the descriptors. I won't enter in details here regarding the results. What is interesting here is to see that it's much more hard for the classifier to detect half cadences than perfect cadences, and this is and it's particularly it's especially because in half cadences you don't have this particular bass move 5-1 that you have on a perfect cadence, which is really recognizable, and in half cadence the bass move can be much more various, so it's more difficult to detect. So here the classifiers that worked the best was a supervector machine. This idea of representing the score at each beat by high-level features, we used it also for another problem than cadence, which was structure identification. With a particular structure which is called the sonata form. So the sonata form is a structure which has been used a lot in the classical era by Mozart, Haydn, Beethoven, and some others. We have a small example here. So you always have three large sections: the exposition, the development, and the recapitulation. And in the different section, you have subsection, primary theme, secondary theme, conclusion, and the same in the recapitulation, but in another key, partially in another key. And the goal of structure identification is to locate where are the boundaries of the sections. So here, we implemented 26 descriptors, which we felt were appropriate for recognizing the structure. We have different type of descriptors regarding patterns, melody, breaks, key change, voice leading. Including some very sophisticated descriptor, like I like this one, the HA. It's the triple hammer blow. I don't know if you ever heard of a triple hammer blow. It's when in classical music, at the end of a phrase, you can have something like da 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 da, and you have this triple repetition that will confirm that yes, this is the end now of this phrase, and something else is going to begin. And it's far to happen constantly. It's rather rare, but when it happens, you know that you're likely to change your section from another section. So yeah, we had some descriptors like that, and the model we used here is a hidden Markov model where the hidden states are the different sections of the piece of the structure, and the observations are the values that are computed by the descriptors. Okay, that was just to illustrate this approach of high-level features on another problem. In classical music, another element of language we feel is important in our team is the texture. So this is a PhD work of Louis Couturier, which is beginning his second year of PhD in the team. So it's sometimes a bit hard to define texture in music in comparison to melody, harmony, or rhythm. I like to illustrate it with the idea of a piano, which is accompanying a melody. So if you need to accompany a melody, you have a chord sequence, and you can place the notes of the chords all simultaneously, or you can arpeggiate the chords, one notes after each other, or you can break the chord. You have different options. Each time it's the same chord sequence, but what changes is the texture. So there is different way to describe, there is different feature to describe the texture. We can talk about the diversity of notes, the density, if there is a lot of notes or not so much. The function, if what we play is intended to be in the foreground or in the background, more accompaniment, or in the lead melody, for example. If there is interaction between voice, for example, is there a melody played at the third or with an octave relation, this kind of things. And to come back on the parallel with text, sometimes when you have to study a text, you're going to distinguish the content and the form of the text. And if you had to do the same in a musical score, you could say that the content would be the melody and the harmony, and the texture would be the form. That's one way to see it. So the work of Louis consisted so far in elaborating sophisticated syntax in order to describe texture in the piano sonata of Mozart. So you can see above each bar a label, which is supposed to explain what is the texture of the bar. So for example, here you have 3H, M1, H2H, which means that you have three notes which are played in homorhythmy, which means simultaneously, and which can be decomposed with one note that has a function melodic and two notes that has a harmonic functions. And these two notes are themselves played in homorhythmy. So that's just an example of how the syntax works. And Louis is now implementing some descriptors in order to predict what is the textural level in an unseen musical score. One of the perspectives of texture is also that it can help a lot for structure detection. For example, when you finish a section and you start a new one, you're likely to change the texture. Louis has also built a kind of bestiary of the most used textures that we get in this repertoire of the piano sonata of Mozart. So we find some very cliché textures here. I like the Alberti bass that some of you might have heard about. And so if I try to sing it, it will be something like do, 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 do. It sounds really scholar and really typical of Mozart. If you focus on the left hand, you can hear it in this beginning of the Easy Sonata. But my favorite example is maybe the one in the Aristocrates that probably you also know, maybe you also heard. Hear it. It's Walt Disney cartoon. I don't know if you ever watched it, but anyway. So yeah, so the following of the work of Louis will consist in work on generative model in order to transfer the texture, which is typical from the Mozart sonata, into an arbitrary score in order to transfer it into this style and to try to generalize this as I did to any corpus, any stylistic corpus for style transfer, essentially. Okay. So now we're going to talk about popular music and more specifically guitar tablatures. So here is an example of a guitar tablature. So on the upper part, you have the traditional staff notation, and on the bottom part, you have additional practice annotations. So you have position annotation. So we have 6 horizontal lines corresponding to the 6 strings of the guitar, and the numbers correspond to the fret at which you play the notes, which means the level of the hand along the neck. And these are useful because on the guitar, like other string instruments, the same note can be played at different places as opposed to the piano, for example. So it's really convenient for the performer to get this information. In addition to position annotation, you have a playing techniques annotation, like bands, for example, this arrows, which tells the player that he's supposed to pull the string in order to modify continuously the pitch, like something like that, which would not be possible on piano, for example. But you have also slides, when you slide your hand, vibrato, hammer on, pull off, palm mute, and a lot of playing techniques that will let you improve the expressivity of what you're playing with the guitar. So what we're interested in this project is to elaborate methods to assist the composition of guitar music. That we feel that it could be great for beginner guitarists to facilitate the access to composition. And also for experimented guitarists to stimulate their creativity and encourage them to go out their comfort zone and try new things that are not in their compositional habits. This is a collaborative work with a company which is in our city, in the same city, Lille. It's Arobas Music. They are known because they do the software Guitar Pro, which is used all around the world to learn the guitar. And they have a nice corpus of 25,000 tablatures in a format which is close to Music XML. including 5,000 tablatures that are very accurately transcribed by professional guitarists that have been paid for that. So it's really clean data. And the first thing we've been investigating in this data was the texture, similarly to what we saw before with Mozart Piano Sonata. And more particularly, we were interested in looking at the function of the guitar, because in pop rock, the guitar can play very different things. So for example, it can accompany, so we call that rhythm guitar. So here is an example. You might recognize maybe David Bowie. So that would be something like, major time to ground control. I'm not a good singer, but I just can't stop to do it there because I love that song. So it's just two chords that are accompanying a melody. And in a position here, we have a melody which is thought to be much more in the foreground. It's an excerpt of a solo from the Pink Floyd. And let's hear a third example. So a piece of Sultan of Swing of Dire Straits. And in this case, it's more difficult to know if it's rhythm guitar or lead guitar. As in rhythm guitar, we have chords. It's clearly following the harmonic scenario, which is here, the chord sequence. But in the meantime, there is some melody click, and we feel that it's written in order to be in foreground, at least during this moment. So in some cases, it's more difficult to decide. And we were therefore wondering if an algorithm classifier could decide whether we are in rhythm guitar or not. This would enable us to improve our understanding of what rhythm guitar is in popular music, but also it would enable to more consistently train generative models that would be intended to assist composition, either in the case of rhythm guitar, either in the case of lead guitar, because we feel like if it's used as a tool by a composer, this kind of system is rather to be used in one of the two cases, but and maybe not in, with all the functions mixed. So David has manually annotated 100 pieces, which is more than 10,000 bars. It was during the lockdown, so he had time, but it was still very courageous. And fortunately, a lot of pieces are just rhythm guitar from the beginning to the end. Some other are lead guitar during all the pieces, and some other are switching regularly. And we identified 31 features that describe what's happening within the bar in terms of notes, in terms of chords, and in terms of annotation specific to the guitar, tablature annotations. And the correlation of these features that are automatically computed at each bar and the manual annotation give us information. For example, the number of notes. So in blue, we have rhythm guitar, and in green, it's other. And we can see that when you have a lot of notes, you're likely to be in a rhythm guitar case, which is not surprising because rhythm guitar features generally chords, and chords have a lot of notes, so it's not surprising. The mean value will tell you that if your end is at the bottom of the neck, you're more likely to be playing rhythm guitar, while when you are at the top of the neck, you're more likely to be on lead guitar. And all guitarists know that. It's because when you're on the top, you're more soloing and you want to access to high notes and this kind of thing. And in rhythm guitar, it's great to play at the bottom because you can benefit from open chords that are generally played at the bottom of the neck. So each of these features would probably not be sufficient to predict accurately if we are in rhythm guitar or not, but the hypothesis is that the combination of the whole features would help to recognize if we are in rhythm guitar or not. And it works quite well using a LSTM. which is applied on the sequence of bars, which are all represented by a sequence of values corresponding to these high-level features. So it was important to use a recurrent neural network here because, of course, when you have a bar which is rhythm guitar, the next bar has a lot of chance to also be a rhythm guitar, and the texture is not changing. I mean, the function is not changing at each bar naturally. So we got a F1 score of 95, which was not so bad, and we know that we could not go too high because of the ambiguous cases, as the one we saw with Diostrait. Sometimes it's just not possible to decide whether it's rhythm guitar or not. And if we want a model that would enhance creativity in the end for generation, it's better also to have examples which are at the border of the corpus of the function in order to be more creative and to do some stuff that are sometimes a little bit almost out of the box, these kind of things. And so separating from our large corpus of tablatures, extracting also rhythm guitar enabled us to approach the problem of texture imitation. So if we come back to our example of Bigo with the two chords accompaniment here, we have two successive chords, C major and E minor. Let's really listen to it. And what we can see on these two chords is that there is a lot of similarities. Even if the notes are not the same, we can see that the rhythm is almost the same. A lot of onsets in common, a lot of duration in common. And the ambitus is similar, not in the same range. We have the same density also, same durations, and we have similar position. As you can see, the frets are between 0 and 3 and 0 and 2 here. So the end will basically be at the same position. So this similarity of texture from one and two adjacent bars give us a feeling that when a composer is writing rhythm guitar music, a lot of time what he will be doing to compose the next bar is to say, okay, I want to imitate the previous bar, but with a new chord. And that's what we call the imitation, texture imitation task. So if we want to formulate in a machine learning framework, that would be given the two blue squares, which is the first bar and the chord of the next bar, could I predict what's happening here? Of course, if the texture is changing, it won't be working, but most of the time, we hypothesize that in a lot of time, so the goal would be to really stay the same. And we see two cool applications to that. Cool potential applications. There is continuation where the composer is inputting a beginning of something and he has chords for the rest and the system is proposing what could come next. And there is also style transfer where the reference texture could be selected by the composer in another piece, for example, and the composer would say, here is my chord sequence, here is my reference texture, can you just combine the whole in order to get my chord sequence, but with this reference texture. So here is the model we tried for this task. So it's a quite simple model. Each bar is represented by vectors that represent the musical time at the 8th note. A 4-bit bar would be represented by 16 vectors. And each vector includes 157 values. 150 are only for the position because you get 6 strings with 25 frets. So it's 150 possible positions. It would be a many-hot vector because you can have several strings that are played. 6 digits for the held strings to indicate that a string is played, but it's not attacked. It's just held from the past, which will let you generate long notes and not only attacked notes. A digit to say that it's a rest or not. And we concatenate to this representation of the bar, a representation of the chord symbol of the next bar with a very standard representation we use in music informatics research with 12 digits to represent the pitch class, 12 digits to represent the pitch class of the bass note, which is great when we have inverted chords. And the 12 pitch class for the other pitch class which are present in the chord symbol. And when giving that, the network is trying to, given this input, predict the next bar, which is in the same format than this one. And so the training data are 10,000 couples of adjacent bars. And again, we have no guarantee that in these couples, there won't be some adjacent bars with completely different texture, which can be messing up a little bit the model. But the hypothesis is that the majority will be similar texture, and therefore the model will finally understand that it's imitations that he has to learn to do. Let's listen to some example of what it gives. So I'm going to switch on GitHub to have a better sound and enjoy what they've been doing with a great sound font. Try to find my mouse. Is it here? So no, probably it says direction. Yeah, got it. Oh no, it's the wrong window. Yes. Okay. So each time on each example, there is 4 bars. So 2 first bars are the 2 original bars as we see it in the corpus. Then we got again the first bar, and the second one has been generated, what the model is predicting for the second bar. So here we are lucky because the second bar is exactly the same as the one. So the prediction went perfectly well. But it's not surprising because we got quite a simple rhythm, and also the guitarist will see that it's extremely common position that we got here, the D major position and the standard A major position. So probably this position have been seen a lot in the corpus during the training, so it was not hard for the model to predict. We can still listen to it. Okay, let's move to another example. So here, the prediction was almost good, but we have some note missing. Let's hear it. And now what has been predicted? Oh, sorry. So I like this example because we want, so what's happening here is that we have a chord just with what we call power chord with just the tonic and the fifth, and which is really typical in blues and in rock music, in this kind of music. The fifth is moving to the sixth, which is the non-chord note, just an ornamentation, which is a stylistic ornamentation. And we really want this ornamentation to be generalized to any of the chords, which is the case here, because here the fifth of the E, which is the B, is moved to a C sharp, so fifth to the sixth. And we see that the model is able to generalize the chords when it's not of the chord, but when it goes outside the chord, just we prefer not to generate anything, maybe not to be mistaken, but it's not working. So that's definitely a track of improvement. Another example. Okay, this one is interesting too, because it uses open chords. So here we can see that it's largely different here and here. Let's hear it first. So the original one. And now what is generated. So in terms of notes, it can sound acceptable, but let's look at the difference. The first difference is on the position. Here, clearly the hand is moving. It's around 10 and 12 frets, and it moves to 5 and 7. And the model here prefers to stay the same place, probably because he's seen a lot of examples where the hand just don't move and try to find solution without having to move too much. So we can understand that. However, one thing which is really too bad is that there is a strong stylistic effect here, which is the use of open strings. The 0, as you can see here, is used again here. And the open string is tricky because you cannot use it equally at any chord. It depends on the tuning of your guitar. And that the model definitely failed to model, to capture how works the open strings. And therefore, you prefer to generate something without any open strings because it's hard to master. Also, I did not mention, but to improve the training, we did data augmentation. And one common way to do data augmentation in music is to transpose in any keys the examples we got. But we were not able, of course, to transpose all the examples with open chords, because if you transpose a chord with open chords, that won't work anymore, except if you have a human hand, which is very long, but it can be complicated otherwise. So that's another track of improvement, trying to model that and maybe finding more data, or maybe helping the model with end rules dedicated to the specific case. So yeah, that's it for example. I realized I could have put also some example where it's not working at all, and for some reason I forgot, but believe me, there is a lot of time where it's not working, so we have a lot of track of improvements. Okay, let's come back to the presentation. Okay, so I'm almost done. Yeah, okay, so these are the formal results. I won't enter in details. I can just, yeah, show that these are the number of bars that have been exactly correctly predicted. So it can seem quite low, 5%, but remember that a bar predicted is about 2,000 values. And if a bar is correctly predicted, it means that the 2,000 values have all to be exactly predicted. Otherwise, it won't be counted in. So we are not here. We have to remember that the goal is not to predict what is the next user. This would be useless, and we don't need that. We trained the model in that way, hoping that it could produce credible bars for a composer who need an assistant, who wish to be assisted by a computer. And we really think that there is much more bars than these 5% that are just credible and that could work, even if there is a lot of improvement still. But so another measure we used is instead of looking at the world bar, we've been looking only each vectors, which give another score, and we've been also specifically look at specific aspects of what has been generated. For example, the position. If the position was the output can be different from what was the real second bar, but the position can be the same. Same for the set of onsets, which would basically give you, indicate you if you produce the same rhythm that was what was expected, and same for the pitch class content. So yeah, so that's almost finished. I just want to share a very small experience we've also been doing with the team like 2 years ago. So we participated to the Artificial Intelligence Song Contest in 2020. It was the first edition. I don't know if you heard about this contest, probably yes. So the original idea of the organizers was to gather scientific artists in order to build a song with the help of artificial intelligence in any possible way. And there was a lot of various ways actually. And to just put this song in competition, have a public vote and jury, AI specialist jury, and have the notes. So this is what we did. This is a musical score that was a result of our work. And a student of our university has been singing it. And we've been manually playing, we've been adding some digital instruments in order to make it work. So the idea was not here to have an algorithm that would generate the final audio file, but rather to make a human composition during which, at some point, the human would use some AI tool in order to solve some problems punctually. So let's hear an extract first. So where did the computer what did the computer in this work? So for the structure, we used a Markov model, which was a simple Markov model, which was trained on a dataset of structures, a Salami dataset you heard of. And the chord sequence was generated by a long short-term memory model trained on chord sequences of the Eurovision dataset. The melody at the beginning and the end of the piece, the hook, was also generated by just sampling, with simple sampling on the model, which was trained on the melodies of the Eurovision dataset. That was one of the rules, by the way, of the game. It was to use as much as possible the Eurovision dataset in order to get something in the style of the Eurovision, whatever it is. And the lyrics were generated with GPT-2 that was trained on all the lyrics of the Eurovision, which enabled us to have very interesting lyrics and very original, like my heart, my love, the world, you know, your eyes, your heart, thank you, my soul. So I think it's really representative of what we got in the Eurovision. And last year, my colleagues in the team also participated to the competition, but with another approach. This time, they collaborated with a professional composer, Sébastien Galuni, who composed mainly instrumental music. And the major difference here is that the model to generate chords was trained only on data of previous composition of the composer. So it was supposed to compose something in the style of the composer, and the composer was able to recognize a little bit of what he did before, but did it done in another way. So it was quite an interesting experiment for him too. And I really love the result, what they did. It's really cool. It's very nice song to work, by the way. So if you look for songs to work like me, this one is definitely good. You can find it on Spotify, and don't hesitate to check it out. And that's all. So if you have any question, I'll be happy to answer.
Thank you very much, Louis. That was also nice music to end with.
Yeah, I could have later, but.
Any questions, either online or from here?
Yes.
I can ask something. First, thank you very much for the talk. I'm pretty interested in the cadence stuff. I mean, because I wonder whether it can only predict the cadence in the end of the music. It's by the way, I mean, half cadence means it ends on fifths, and the full cadence is ends on the roots.
Right.
Am I correct?
Yeah, exactly.
So it only predicts at the end of the piece, or
no,
the phrase, or every bar, or.
So there is in this kind of music, in this repertory, like quartets, string quartets of Haydn and fugues from Jean-Sébastien Bach, there is systematically a cadence at the end of the piece. It's right. But somehow we don't need to detect it because we know it's here. A strong majority of cadences were in the middle of the piece. So the game was more to detect this one, because otherwise we could have a classifier that only detecting that the piece is ending. Probably we don't need a strong classifier for that.
Okay, so it can predict, say, like a ends, let's say a list of fifths.
A typical fifth progression would certainly help the model to suggest him that it's a cadence. But the problem is that we have a lot of resolution, like 5/1, or we'll have a lot of 2/5/1, which are actually not cadences. And that's the problem. We began with a model with a lot of false positives, because basically first versions were always, we began actually with a rule-based model before going to machine learning. And the rule-based model, first version were always labeling a cadence where we identify like 5/1 or 2/5/1 or 4/5/1. And that's the moment we realized that there were so many places where 5/1 occur, but which are not cadences, because the melody is continuing and clearly not stopping. So, and that's when we realized the complexity of the task. So, and the necessity to mix different features that are harmonic, but also rhythmic, voicing, and the different things I've been showing. So I know things that really machine learning and a lot of diverse features, mixing diverse features is really necessary to resolve it. But it also depends on the repertoire. That might be something specific in Bach fugues, for example. or in the string quartets also, but maybe in some music, maybe in some other classical repertoire, the cadences are much more clear. So yeah.
Yeah, I think a lot of the work is really interesting. Yeah. Do you plan to do something with the melody that you've extracted as well from the Guitar Pro data set, or are you just focusing on the rhythm?
So initially, we really wanted to divide the work like rhythm guitar and melodic guitar. And after all, we realized that most of the melodic guitar was solo guitar. And we also felt that artists might more not be as interested in being assisted for solo, because a solo is generally really, it's coming from inspiration, and I have more, it's more difficult for me to imagine that a guitarist would require an artist would require a computational tool for such a creative activity, where probably wants to master the whole process. That's only a personal feeling, and I might be wrong. It might depend on. It might be different for every guitarist. But and also generating solo would it would be very close to a lot of work in melody generation. So I think we could benefit from a lot of things that have been done before if we wanted to go into that. And for accompaniment generation, it was a little bit different, and we also had the feeling that for beginners, it could be interesting. Also, I didn't mention, but it could be interesting for non-guitarists that want to compose music for different instruments. To have, typically, a non-guitarist who wants a guitar in his song will probably call a guitarist to play the solo. But if it's only accompaniment, maybe you don't want to call a guitarist. So that would be another reason to go in accompaniment. So we haven't planned so far to go on melodies, but we also try to often discuss with the company, because they know the guitarists better than us. I mean, they work with guitarists since 25 years, even if they're not in research, they know what they want, because they hear the feedback regarding the software, they know the tools they want, and they know what they use the software to. So yeah, maybe in the future that could be, but we will have to imagine how such a tool could be used in the end in the software. Because, for example, a question we had is, at some point we say, yeah, but someone told us, a specialist of guitar, tablature notation is rarely used during composition. And generally, tablature is used after the composition to keep a memory of what has been composed, but you don't need the notation to compose, at least in popular music guitar, contrary to classical music, where people are really composing with a notation. And so we try to think, so our hypothesis would be, when you come to the notation, artificial intelligence functionality might suggest you alternative, interesting stuff, and might maybe change your mind on some stuff. And this can probably happen for accompaniment. But if we go in that for solo and melodies, we'll have to think about how could this functionality be integrated into the composition process? At which point the composer, it would make sense for him to say, no, I can easily use a functionality. It would make sense. Is it during the notation or during the composition? Or so, but what could be great if we go into that we have nice data, and solo are particularly interesting from the stylistic point of view, because they handle much more stylistic feature on the guitarist than rhythm guitar. Rhythm guitar is much more standard, much more homogeneous, probably also more easy to train a generative model because it's more consistent. But solo, yeah, you might have very interesting stuff that by mixing different styles of very famous guitarists, if you get enough data and you find a way to maybe augment a little bit this data. But yeah, so very nice challenges here, a lot of things to think about, yes.
You have a question? No? No, you just thank Louis. Yeah, I thought it was
Thank you.
very interesting.
Thank you too. Thank you. Thank you.
Chitra from NUS, she's saying, thank you for the great talk. The work on music texture was very interesting. From what I understand, a combination of melody and harmony define the texture of the musical pieces. Could you also talk a little bit about how you would define texture for popular music?
Great. That's okay. First, regarding the comment on texture, it's really interesting. Thank you for that question. Texture is a combination of melody and harmony. It's true when we look at the score, because a lot of time in score we just have a melody and harmony which is playing somehow, and in the world we can have an abstract point of view which will be the texture. I try to see the texture as something else rather than the combination of the other layers, harmony and melody, I mean, because it seems to me more easy to study it like that. And also it enables to keep melody and harmony outside, because there is so many work on that. It can be complicated to try to make them, but that's an interesting point of view. Regarding pop music, so pop music is so diverse that we probably have a lot of texture in there, and probably a major difference we have with what we are doing with Mozart piano sonata is that we can have in pop music a lot of instruments, and the texture will obviously result from the combination of very different instruments that can play very different things, which will make the study of texture in pop music much more hard because it's less consistent. And a motivation for going into Mozart piano sonata was, of course, that we had a lot of data that were really consistent in terms of style. So it's more easy to study, it's more easy for training models and these kind of things. So texture in pop music would require to have a lot of data, would be consistent enough, I guess, in terms of texture, in terms of style, I mean, and probably to have an approach to mix these different instruments and their different functions, and to know, for example, that the bass has a really different function than the piano, for example, than the keyboard, and to separate this information somehow. But I think like often in our field, the key is the data. I mean, the data set you get, depending on the pop data set you get, you probably approach the texture in a different way. But that's an interesting question, and I think it's a question that is more and more popular in our community, in music generation, especially in multi-track music generation. So probably we'll hear a lot about it in the next years, I guess.
Something like a language model, like a mass. In NLP, you do a mass language modeling where you take away words, so and then you try to make the machine to predict the missing words. So in music, we do something like that to get the embeddings of notes of phrases. And we also do white pair encoding in language modeling. So you merge letters with like the most common combination of letters together to produce encoding. So I'm not sure. I think we should do that here.
Yeah, that's extremely interesting remarks. So for the first one, regarding masking, so I guess you're talking about things like BERT models, and I think there's a lot of works, community. Like I think I saw at least 5 papers like MIDI BERT, Muse BERT, Music BERT, Harmony BERT, Melody BERT. I don't know. There is a lot of people who tried. So your idea perfectly makes sense, and it's true that it's typically like by masking some part of the sequence, it's a good way to train like a general model that which you can use maybe later for transfer and these kind of things. So that makes perfectly sense. And regarding your second question, it's perfectly pertinent, and we're actually working on that. So we have an intern it's too bad. I could have mentioned his work, but he's working on tokenization, on a way to tokenize music. And one part of his work is actually to think about applying byte pair encoding. So it's in my opinion, it particularly makes sense to apply these kind of things, because in NLP, another difference I could have mentioned is that we have a segmentation which is naturally given by the words. And we don't have words in which are given by blank space. And we don't really have blank space in music. We just have notes. And in this sense, I feel that the notes in the musical score are more comparable to the characters than to the words. Because in the words, you have semantic and a lot of things. In a note alone, it's more comparable to a lonely character. When you take it alone, it doesn't make any sense. So the segmentation is a real question in music. And sometimes when we apply NLP to music, we forget that we're just, it's word, but they are so different. Musical token and a textual token are so different in terms of abstraction, of meaning and semantic. So yeah, the idea of byte pair encoding will, as we were approaching it, will be to start from a large corpus of music and in a given style, and see if some musical tokens are very frequently following each other. And if you very often have this token, musical token, which is followed by this token, then you replace the two by a new token. And if you iterate that a lot, you would have more and more token, but also it would be more style dependent. But in the meantime, if you want to use it for generating music, then it can grab some more abstract things, but you will be stuck in this style, but you probably generate some more interesting things. So yeah, I completely agree. That makes perfect sense in my opinion. Yes.
Yeah. All right. Thank you everyone for joining online. I'll end the Zoom meeting now. Yeah. People say thank you.
Thank you very much.
Rigo is here too.